Okay, good morning or afternoon. We're going to go ahead and go over the notes for sound. I'm going to try to cover everything as quickly as possible. You'll notice that the things that are in red font or green font are the most important things, so make sure you jot those down or go back and watch them. There are going to be a few questions in between the presentation, so make sure you answer those when they pop up. One final reminder, remember to let the Edpuzzle play till the very end. If not, it will not mark it as turned in. So make sure you do that. So we're going to talk about the origin of sound and where does sound come from. So the source of all sound is due to a wave of vibration. So there has to be some type of vibration for the sound wave to actually occur. If you think of like a piano or a violin or a guitar, those sound waves are produced by the vibrating strings, right? If you think of like a guitar, there's little strings that you pluck, those strings vibrate back and forth, and that's where the sound is created from or produced from. If you're in band and maybe you play a reed instrument such as a clarinet or a saxophone, what happens is the reed in the instrument vibrates back and forth in the mouthpiece, and that's what produces the sound. Even you talking or me talking right now, what's actually happening is there's a vibration in my vocal cords. So if you try talking and you put your hands up against your throat, right, you can kind of hear the vibration, especially if you make a sound like an ah sound. You can kind of hear it, you can kind of feel it a little bit. Now, in all cases, doesn't matter what you're talking about, the original vibration stimulates into something more massive. So if you think of like my vocal cords vibrating, that vibration is causing the air around to vibrate as well, and that air that vibrates as well also causes the sound to occur. If you're thinking of like a guitar, right, it's going to produce a vibration on the guitar itself, right? So the string produces a vibration on the guitar itself, and that produces an even bigger sound. If you think of like a saxophone or a clarinet, the vibration occurs in the mouthpiece, but then that entire vibration vibrates throughout the entire column of the instrument, and that produces a bigger sound. So this vibrating material then sends a disturbance through its surrounding medium, which usually is air, in the form of longitudinal waves. The frequency of the sound waves produces equal frequencies of the vibrating source. What that means is if you think right now, or if you can think of, imagine me if we were in the classroom and I was speaking in front of the classroom, what's happening is my vocal cords are vibrating back and forth, and that vibration moves through the air around, right? And it's traveling in all directions and through the air, okay? Oops, in the form of a longitudinal wave. So depending on how high pitched or low pitched those vibrations are, it's going to also determine its frequency, right? So another word for frequency is pitch, or another word for pitch is frequency. And usually that depends on the object that's making the noise. For example, your vocal cords change frequency based off of how open or closed the vocal cord is. If you're someone that's like in band or in orchestra, then you'll notice that depending on where you hold the strings down on the guitar or what valves are closed on like a clarinet, it's going to determine the pitch of sound that the instrument makes. Okay, so you can have really high pitched sounds like me, like my voice, it's very high pitched, right? That means it has a very high frequency. But then if you have something really low pitched, something like a foghorn, then that has a really low frequency. And you can also say it has a low pitch. Now, normal people, young people such as yourself, can hear pitches in a wide variety of frequencies that can range anything from 20 to 20,000 hertz, with 20 hertz being something really deep and low, and then 20,000 hertz being something really high pitched. Are there frequencies other than those? Yes. If you think of like dogs, if you have a dog whistle, if you've ever blown in a dog whistle, you can't really hear it, but your dogs go crazy because they can hear it. They can hear frequencies up to 40,000 hertz. but you can only hear up to frequencies of 20,000 hertz. And believe it or not, as you get older, your hearing range shrinks, meaning you're not going to be able to hear those really high frequencies. You're not going to be able to hear the low frequencies as well. There's an app you can get on your phone, or there's like this little test that you can do, which is really neat. You just kind of Google hearing test, and you're able to hear to see what's the highest frequency and what's the lowest frequency that you can hear. And something neat is you can do it with yourself, or you can test it on yourself and then test it off on maybe like your parents or your grandparents, and you're going to notice that their hearing range is not the same as yours. They're not able to hear as well as you probably will. Why? Because that's just over time your ears, they don't work as well, and you're not going to be able to hear those frequencies. Now, if we're talking about frequencies, if there's anything below 20 hertz, meaning less than what a human can hear, less than what a normal human can hear, then those frequencies are called infrasonic. Sound waves with frequencies above 20,000 hertz are called ultrasonic. So infra, smaller, right? So infra means smaller than, so smaller than 20 hertz. Ultrasonic, ultra means greater than, so greater than 20,000 hertz. Here it is. Humans cannot hear infrasonic or ultrasonic waves. Dogs, however, can hear frequencies of 40,000 hertz or more, meaning that they can hear ultrasonic waves. Bats can hear sounds over 100,000 hertz, frequency of 100,000 hertz, meaning they have super ultrasonic hearing, right? They can hear all types of noises. So sound in air. So far, we talked about the origin of sound. We talked about pitch and frequency. Let's talk a little bit about how sound actually travels. So if you clap your hands, you're going to produce a sound that goes in all directions. Remember, sound is going to travel in every direction. And what's happening is each particle is moving back and forth along the direction of the motion. So what ends up happening is sound isn't a wave like a light wave, how it has a photon that it can actually travel. It doesn't travel through actual. When you produce a sound, you're producing a disturbance in the medium that you're producing the sound. Okay, for example, me talking, I'm producing a disturbance in the air around me. You clapping your hands, you're producing a disturbance in the air around your hands. You're not actually producing anything else, like there's no photons being created or any other particle being created. It's just the air around that's moving, right? And it's actually going to move similar to this slinky right here in a longitudinal format, meaning there's going to be areas where it's really compressed and areas where it's really far apart. So if you look right here, those the analogy that's given is a door opening and closing, right? And when it's opening, there's like a little window on the other side. And when the door is open, a compression travels across the room. You'll see that there's like air that travels from the door to the window. When the door is closed, a refraction travels across the room, meaning that the air is going to go back. So a pulse of compressed air is a compression. A pulse of low pressure air is called a rarefaction. So if you go back, the compression is where it's really close together. The rarefaction is where it's really far apart. And so here you can see air molecules moving. So here's a little video, just a quick little animation. You can see there's like a little speaker, and they're going to play a noise on the speaker, a sound on the speaker. And you'll notice that all of those air molecules are moving as the sound travels, right? That is how sound travels in air. It's all of the air molecules bumping into each other. So I produce a disturbance that causes the air molecules to move, and those molecules bump into the next ones, and then those bump into the next ones, and so on and so forth. So for all wave motion, it's not the medium that travels across the room, but a pulse that travels. And if you pay attention to like the first air molecules right here. These air molecules right here just moving back and forth. They're not traveling themselves, meaning the air that comes out of my mouth when I talk isn't going to travel across the room. It's just going to bump into the molecules next to it. Now, believe it or not, sound can travel in mediums other than air. sound can travel in solids, liquids, and gases. So most of the sounds that we hear are transmitted through air because that's the medium that we're around. However, depending on whether your sound is traveling through a liquid like water or through a metal like a chain fence, it it can vary on how fast it travels. So remember, because those molecules, sound is just a disturbance in the medium, and that disturbance is those molecules bumping into the next ones, bumping into the next ones, bumping into the next one. So if you think of a solid, liquid, and a gas, like the air that's around us, all of those molecules are very far apart from each other. So it takes a lot longer for one molecule to bump into the next, to bump into the next. Granted, it does happen fast, but it doesn't happen as fast as a liquid, right? In a liquid, those molecules are closer together, meaning they're going to bump into each other faster. And in a solid like metal, those molecules are really compact, meaning that they're going to bump into each other even faster. So, just based off of that, you should be able to tell that sound is actually going to travel faster through a solid than it is through a liquid than it is through a gas. So, an example of this is if you put your ear next to like a fence or maybe like a railing on a pole or something, and you tap on it, you'll be able to hear it a lot faster running through the railing than you do as it runs through the air. So the speed of sound differs in all materials. In general, sound is transmitted faster in liquids than in gases and even faster in solids. Sound, however, cannot travel through a vacuum. Now, if you remember, if you think of space, space is a vacuum, right? There's no air molecules, there's no extra matter floating around. Because there's no extra matter, because there's no molecules, sound cannot travel because sound is just a disturbance of those molecules. If there are no molecules, then there can't be a disturbance. So a transmission of sound requires a medium. There may be vibrations, but if there's nothing to compress or expand, then there can't be no sound. So if you think of like Star Wars, you hear like, you see the people with their little like, what do they call them? Their little X-wings, and they're like pew 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 pew. You wouldn't really be able to hear that. Um, Another thing, if you scream, so I guess something that I always think of is if you scream in space, would someone be able to hear you? No, someone else wouldn't be able to hear you. Would you be able to hear yourself? Kind of, because your vocal cords are creating that vibration, right? But that's part of your body. So technically, that vibration could travel through your whole, like through your head, through your skull, through your skin, into your ear. So you might be able to hear some variation of a noise. It might not be exactly the same, but you should be able to hear it. Another neat thing, have you ever thought of why you don't sound the same on a recording than how you hear yourself, right? When you talk, you hear yourself a certain way, but then when you listen to a recording of yourself, you're like, whoa, I sound different. So what's happening is when you're talking, there's sound that's coming out of your mouth, traveling in the air around you, and it can actually travel around to your ear. But at the same time, sound is also traveling, like I said earlier, through your skin, through your bones, through your skull, into your ear. So you're hearing it through two different mediums, right? It's traveling through two different mediums. Now, the reason you actually sound a little more high pitched in real life than you do what you hear yourself is because of the density of your skin and the density of the bones. It's different than the density of the air. So it actually changes that frequency. Next, so we're going to continue to talk a little bit about the speed of sound. So the speed of sound compared to the speed of light, hopefully you know that the speed of sound travels much slower than the speed of light. So a perfect example is like thunder and lightning, right? Thunder is both of the objects crashing into each other. The sound you hear of both of those clouds crashing into each other. The lightning is the light that you see between the collision. You usually see the lightning first and then you hear the thunder after. Why? Because it takes longer for that sound wave to travel than it does for a light wave. The speed of sound in dry air at 0 degrees Celsius is about 330 meters per second. Okay, so sound still travels really fast, 330 meters per second, but nothing like light, right? Light travels at 300 million meters per second, so a lot slower than light, but it's still pretty fast. It averages to about 1,200 kilometers per hour, so definitely very quick. Is it possible to go the speed of sound? Yes, it is. Have you ever heard of Mach 1? Right? When you watch movies, sometimes they say, like, oh, we've reached Mach 1. That's the speed of sound. If you've ever been on an airplane, you've traveled faster than the speed of sound because airplanes do travel faster than the speed of sound. You look up, sometimes you hear an airplane, you look up and you see it, and you're like, wait, it sounds like it's over here, but it's actually over there because it's traveling faster than the sound being emitted or than the sound reaches your ear. That's crazy, right? So if you increase the temperature, you're going to increase the speed of sound. And that makes sense, right? Because it's all those molecules bumping into each other. And when we talked about heat, we learned that when there's an increase in temperature, the kinetic energy of the molecules increases. So they're moving faster. And if those molecules are moving faster, then it's easier for them to bump into each other. Now, the speed of sound in a gas also depends on the mass of its particles. So the lighter the particle, the faster it moves, the easier it can transmit sound. The heavier the particle, then it takes a little longer. Sound also depends on the elasticity of the object. So the elasticity is the ability for the material to change shape when a force is applied, and then it resumes to its initial shape. So steel is very elastic, whereas putty is very inelastic. So sound's going to travel better through something elastic like steel than it is through putty. Now I want you to think, how far away is the storm if you know a 3-second delay between a lightning flash and the sound of thunder? Hopefully, you should know that the speed of sound in air, not at 0 degrees Celsius, but at room temperature, is about 340 meters per second. The distance is 3 seconds away, so all you would do is multiply 340 times 3 seconds, and you end up with about 100 meters or 1 kilometer. So for every time you hear lightning, for every 3 seconds that it takes for you to hear the thunder, it's about 1 kilometer away. Next, we're going to go over loudness. So we talked about frequency, we talked about pitch, but now we're going to talk about loudness. So loudness has to do with the amplitude of the wave. It's how intense the sound is. And loudness is usually measured in decibels. When we're talking about loudness, I'm talking about volume, right? Pitch is like how high pitched or low pitched it is, right? Like But loudness refers to the volume. Like, are you going to increase the volume, decrease the volume? That's what loudness is. And like I said there, it's measured in decibels. So starting with 0 at the threshold of normal hearing, if you increase each 10 decibels, means that the sound intensity increases by 10. So a sound of 10 decibels is 10 times as intense as a sound of 0 decibels. 20 decibels is not twice, but 10 times the intensity of a 10 decibel or 100 times more intense than 0 decibels. 60 would be like 6 times 10 times more intense, right? So you just have to see, it goes by factors of 10. So it's a logarithmic type of trend. And here you can just kind of see the decibels. A hearing threshold is 0, right? Normal breathing is about 10 decibels. A whisper is about 20. In a library, it's kind of quiet, so it's about 40. Normal speech, like right now, I'm talking about 60 decibels. If you go outside for street traffic, you're looking at 70. But then look at like a jet engine when it takes off, you're looking at 140 decibels. So it is possible for it to get louder and louder. Hearing damage does begin at about 85 decibels. So if you look at that, you're looking at maybe like a factory type of setting. Even outdoor busy street, you might be able to get a little bit of hearing damage. Now, hearing damage can't be reversed, but it does take a while for you to get permanent hearing damage. You can get you can get a small damage with exposure to like really loud noises, and it does take a while for your hearing to go back to normal. But long term, hearing loss is possible if you listen to, that, I know you probably hear it when you were little, like, don't listen to really loud music or you're going to lose your hearing. Yes, that is 100% possible. You can lose your hearing, but you would have to be exposed to it for very long periods of time. Maybe if you're someone that like goes to a rock concert once, you probably won't experience any damage. But if you play at a rock concert, if that's your career, then you do need to take care of your ears because that long-term exposure can cause you to have damage. Um, just something to remember: when an object is composed of elastic material, it is disturbed, it vibrates at its own special set of frequencies, which together form a special sound. That special sound is actually called the natural frequency. So the natural frequency is the frequency at which an object vibrates when it's disturbed. Think of like a glass, a wine glass, right? If you like hit it with your finger, it makes a specific noise. Depending on the shape of it, it might make a different noise. That's all its natural frequency is. Right now, if you hit the table, it's going to sound different than if you hit maybe like your bed, or maybe if you hit the wall, right? They all have different sounds that they make. That's their natural frequency because those atoms vibrate um, at their own rate. Now, the natural frequency actually depends not just on the elasticity of the object, but the shape of the object as well. Think of bells. They're all made of the same material, but depending on the size of the bell, it can have a different noise, right? It can have a higher pitch or a lower pitch. So not just the shape, but the elasticity, the material it's made out of. Most things, right, they are all made out of atoms. They have some type of springiness and they vibrate at one or more natural frequencies, right? Like your body is made out of multiple atoms, so you don't have a natural frequency. A natural frequency is one at which a minimum energy is required to produce a forced vibration, and the least amount of energy is required to continue that vibration. So I'm going to show you something that's vibrating at its own natural frequency. But before we go over that, I need to continue and I need to go over resonance. But before we go over resonance, I need to go over a forced vibration. So a forced vibration occurs when an object is made to vibrate by another vibrating object that is nearby. So if you have, for example, two tuning forks, and I wish I had two tuning forks to show you, but if you had two tuning forks, you could, have one tuning fork move and make a noise, and if you bring another one close enough, it's going to force a vibration on it. It's going to cause the other one to move. If you think of maybe like playing a speaker in like water, you'll notice that the water around it's also going to move, even if the speaker isn't touching the water itself, right? It's going to force a vibration onto it. So resonance. So if a frequency is forced and it matches an object's natural frequency, then resonance is going to occur. For example, if you're swinging on a swing and you pump your legs at the perfect frequency, right, at the perfect rate, then you're going to resonate and that swing is going to swing further and further and further up, right? Just because you swing your feet doesn't mean that you're going to swing higher and higher. You have to match the natural frequency of the swing itself, right? That's what resonance is, when you match that frequency to force a vibration onto an object, then it's going to resonate. So here you have an example of an object resonating, right? You see the tuning fork is resonating back and forth and back and forth and back and forth. Another example of resonance is the Tacoma Bridge. So resonance occurs whenever successive impulses are applied to a vibrating object in rhythm with its natural frequency. And so let me tell you a little bit about this bridge while the video plays. So there was this bridge in Tacoma, Washington, and essentially what happened was they built it. It wasn't structurally sound to begin with, but it was built out of, concrete and metal. And it was a really, really windy day, and the frequency of the wind was equal to the natural frequency of the concrete that the bridge was made out of. Hence, this crazy scene from a movie appeared. And I know what you're thinking. That's not real. There's no way that's real. That's totally fake. No, it's real. It's real. It happened. I think it happened in like the 60s or something like that. And it just like freaked everyone out because look at this. This is supposed to be a structurally sound, object, and it's swaying like it's made out of elastic. Let's see if I can. Do you see it? Like swaying back and forth. That's crazy. Why? Because the wind was just blowing at that perfect frequency. Now there's like all these tests that they do, not just when building bridges, but when building really, really tall buildings. They have to double check things like this. So incidents like this don't happen. Thankfully, no one was injured. No human was injured in this particular incident. However, if you pay attention, there's a little car that's left there. There was a dog in the car. Oh my gosh. So someone tried to go get the dog. The dog wouldn't come. It's crazy, right? It's like that possibly couldn't have happened, but it did. I'm not going to show you this video. I'll post it as something extra for you to watch if you want to. It explains it really well, and it has a really good visual for you to see. The last thing we're going to go over is interference. So we talked about interference when we talked about light. Now we're talking the same type of interference, but we're talking about sound. So for sound, remember we don't have crests and troughs, but we have compressions and rarefactions. So when two rarefactions overlap or two compressions overlap, then they're going to produce a bigger wave. If you have a rarefraction overlap with a compression, that would be like a trough interfering with a crest, then it's going to decrease the size of the wave. So when two crests or two troughs overlap, or two compressions and two rarefactions overlap, you're going to have constructive interference. But when a trough interacts with a crest, or when a rarefraction interacts with a compression, you're going to end up with destructive interference. So here's like a little example. You can see the pictures, right? When the two crests line up, it makes a bigger wave. Same thing with sound waves. You'll see they get more intense. Over here, you have destructive interference when a crest interferes with a trough, right? So they destruct. The same thing happens right here. That's actually how noise canceling headphones work. So again, this video, I don't think the sound's going to work on this video, but I will post this video for you to see. Just it's a little snippet, 50 seconds, 1 minute, less than a minute of it explaining how noise canceling headphones work. And with that, we're done. Have a great day. Hopefully you're able to watch the whole video, and see you tomorrow.